Hi, in this class, we're going to be learning about data structures, algorithms, and how to think about those data structures and algorithms so that we can learn how to choose the best tool for the job. At a fundamental level, the primary objective of computer programs is basically just to manipulate data. If you think about it, all any program does is just manipulate data. So learning about data structures and algorithms really helps you to understand how to organize that data and how to operate on that data. In order to be successful, we'll need to start thinking about how we can analyze and compare these data structures and algorithms to each other. We will be approaching the problem analytically, meaning we'll be timing algorithms, we'll be measuring how long it takes things to happen, but we'll also approach it logically. We'll be thinking about how algorithms and data structures operate at a bit of a more abstract level. And again, the objective of all this is so that we can develop a framework by which we can discover the trade-offs between different algorithm containers and compare them and ultimately know how to choose the best one for the job. To begin with, we're going to start with perhaps one of the most simple algorithms that there is, sequential search. So this will sort of help us to set the stage on what we're going to be doing during the rest of this class. So let's talk about the simple or maybe not so simple problem of finding an element in a container. So there's a container is just a way of saying data structure. It's a special object which holds other objects. And typically a container holds several objects, all of which have the same type. So if you think about an array, it's a way to store, several objects of the same type. You can have an array of integers, for example, which holds a bunch of integers. So can we take a container, any kind of container? We'll get into specifics about the different kinds of containers later. Right now, we're just going to mostly be thinking about a list. Okay, and so can we take a list and can we find in that list if a certain item is there or not? So if you think about it, if you were given a shopping list or something and I were to ask you, okay, here's the shopping list, you're going to the grocery store, can you just double check if oranges are on the list? What you're probably going to do is you're going to start at the top and you're just going to scan down from the beginning towards the end until you see oranges. If you see oranges, you're going to say, oh yeah, here it is right here. And if you don't see it, you're going to say, no, it's not on the list. So basically what we're just going to do is imitate that very natural behavior of scanning the list from the front to the back to check if something's there. What we're going to do is we're going to write a function, we're going to call it find, and what it's going to do is it's going to perform a linear search or a sequential search. Now I'm just going to go ahead and put this in a namespace so that we don't get any collisions with names in the standard library. Namespace my. So we're going to write a function called find, and we need to think about what this function is going to return. So for now, let's go ahead and return a Boolean value, either true or false. True if the element was found, and false if it was not found. Okay, so now let's think about how we're going to represent our list. So there's several ways we can represent a list. We could use a raw array, we could use a standard array with standard library array, which is slightly different, or we could use a standard library vector. To keep things simple, I think we're just going to go ahead and use a vector for now. So let's take that vector as a parameter. And for now, we'll just keep things extremely simple. We'll have it be a vector of integers. And let's just call this list. And then there's going to be a specific integer, let's call it item, that we're going to be looking for in this list. Now, in order to do this, I'll also need to include vector from the standard library. Okay, so this is the signature of my function. This is the find function that I'm going to write, and I'm going to write a sequential search algorithm. One other thing that I will need to do is I will need to call this function, and I'm going to need to have a vector of integers. So let's just go ahead and create a vector of integers. So vector of int, let's call it values, let's just give it another name, and let's just give it a few values. I'm just going to go ahead and add these values to the vector. And now to the implementation of this find function. We're going to start with the most simple approach, the naive approach, and we're just going to write a simple for loop. So we're going to start with int I equals 0. Now, I should mention that when you have a contiguous list of values, like vector or array or even a raw array, Typically, one of the main access patterns for the elements in that list is by index. So these data structures keep track of the elements in a contiguous block of memory, and first element as at location 0 with index 0, and then the next element is at location 1 and 2 and then 3 and so on and so forth until you enumerate all of the elements in the container. A lot of these data structures are index based. So what we're going to do is we're going to write a very simple for loop. It's going to start with index 0, so I is going to represent index. So index is 0 while I is less than list.size 1 minus the size. Okay, so if the size is 10, here we have a vector of 10 values, then size will be 10, so we're going to count 0 through 9. The indices will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's why we always say I is less than list.size. Through each element, now how do we get access to the element? So we're going to say list.atI, so this gives us access to that element. And what do we want to do with that element? Well, we want to check if it's equal to item. So I'm going to say if list at I is equal to item, return true. Otherwise, I keep going, I keep searching until I get to the end of the list. So after I've gone through the entire list, I've gone through all the indices, and I haven't found it, because if I did find it, I would have already returned from the function. If I make it this far, it means that I have not yet found the element, in which case we're going to return false. All right, so this works. Let's go ahead and call it and see what happens. So if my find, okay, and then we're going to pass the vector, and let's look for the value 2. So if invoking this function returns true, let's just go ahead and print out the value was found. Otherwise, we'll just go ahead and print out the value was not found. Okay, we can run this code and run it. And as you can see, the value was found. So we did find the value. And if I go back and run this code again, and suppose I put the value of 12, I'll have to recompile this. But if I search for the value of 12, and then I run the program, you will see that the value was not found because there's no 12 in that list. So this is working correctly. Now, we're going to spend the rest of the lesson making improvements to this function, so I would not at all suggest that this is a great implementation, but it is a fully functional and correct implementation. In other words, this find algorithm performs a sequential search on the list, and it finds the element if it's there, and if it doesn't, it returns false. So this is correct code. We're going to spend the rest of the lesson improving this. In particular, we're going to make some improvements that follow some well-known patterns that we see with C++ code, and we're going to imitate the way that the standard library works. Let's think about some of the ways that we could improve this. All right, so there's several critiques we might have of this implementation. First of all, it only works on vectors of integer elements. Okay, so it would be nice if we could make this algorithm that we've implemented work on vectors of strings or vectors of characters or any other data type. Another major flaw that I can think of is that it doesn't share the information about where the item is that was found. So the algorithm, as it's operating or as it's processing list, it does at this point in time when it returns true, it does know the exact index where the item was found in the list. And that could be some really useful information. Perhaps the user of this algorithm that we've written wants to know where the item is. So if it is in fact in the list, they will know how to access it. They will know where it is. That's an extremely useful thing to know. But right now we're completely losing or throwing away that information. That would be a major improvement, is to not only return true or false indicating whether the element was found, but to return the position at which the element was found, or at least a way to get that element back out of the list. So let's start to think about how we can address these limitations. One of the main things we're going to take advantage of is iterators. So In C++, the standard library is designed such that every single container has a special related object called an iterator, and the iterator encodes how to move through the elements of that container. So the information about how the container is, how it stores its elements and how data is laid out internally is not something you need to think about as a user of the vector class, right? You don't need to necessarily know that data is contiguous or not in order to just make use of standard vector, but you eventually reach a point where you need to access the elements in the container, and normally you would have to understand some of the internal structure of vector. But the way that C++ works is it provides, along with the containers, the iterators, and the iterators encapsulate that information about how to access and move through the elements of that data structure. So we're going to use iterators in order to access the elements of the container that we're searching through. All right, and you can think of an iterator conceptually kind of like a pointer. A pointer is something that refers, or even like a reference, right? It's a variable that refers to another value. And with a pointer, what you do is you dereference that pointer in order to gain access to the object it is pointing to. Same thing with an iterator. With an iterator, what you do is you dereference the iterator and it returns back the actual element from the container that it's referencing. So an iterator is a kind of reference or pointer, but it's not exactly the same thing as a pointer. An iterator also knows, and this is really important, how to move from one element to the next. You can use the plus plus operator or the minus minus operator or some built-in functions, the next function or the previous function. When you call these functions with the iterator will move to the next value in the data structure. Okay, and the other really important thing that iterators do, or the way they're designed, uh, is that they are allowed to not refer to any of the elements of the container at all. And this might be a little bit surprising to somebody who's new to this design, but it turns out to be an extremely useful uh, aspect of iterators. Just like a pointer can either point to a value or it cannot point to anything at all. The fact that a pointer has this special null state, which we call the null pointer, right? The fact that it has this special state allows us to use pointers to optionally represent data. So either it's a null pointer and it doesn't refer to any data at all, or it's not a null pointer and it does refer to actual data. And this allows us actually to encode 2 bits of information into this data type. So if the pointer so if we ever have to ask the question, is something there or not, we can use this optionality to encode that information. In the same way, iterators have this special sentinel state, and it's usually used to indicate the end of the range. You have an iterator called standard begin, which refers to the first element in the container, and then typically you have another iterator called standard end, which doesn't refer to any elements of the container, but which is used to signal, kind of as a sentinel, that you've reached the end of the list. So what you do is you take the begin iterator and you just keep calling next on it, and it keeps moving through each element of the list until it gets to the end of the container, and then it becomes the same value as the standard end iterator. So taking all of this that we've just discussed about iterators, let's go ahead and replace our index-based approach with an iterator-based approach. But hopefully you'll see that there's a lot of benefits to it. All right, so what do we need to do in our for loop? So instead of starting with index 0, we're going to start with the begin iterator. So let's just write this, auto it equals standard begin of list. In fact, what I want to do is say standard c begin. This will take a constant iterator to the beginning of the list. Okay, constant because we really don't need to change the elements of the list. Okay, so begin and c begin, if you call these functions on a list or on any kind of container in the standard library, they will return the iterator which refers to the first element. And notice the data type of this iterator is a standard vector of int const iterator. Okay, and so long as that iterator is not equal to the iterator you get back when you call end or cend on the container, so long as that's not the case, because if iterator does equal cend, that means we've reached the end of the list. So as long as it's not equal to that, we're going to do some stuff, and then we're going to increment. We're going to increment the iterator. Okay. So here's what our for loop would look like. And then what do we do inside the for loop? We're going to have to just do something slightly different. So instead of saying list at index I, we're going to say if the, and then we're going to dereference the iterator. So if the item, okay, in the container, so dereferencing the iterator gets back the actual integer it's referring to. If that integer is equal to the item that we're looking for, that's when we return true. Okay, so no more indices. Now we're using the iterator. So we dereference the iterator. If the thing at that iterator, okay, if that integer equals the item that we're looking for, we'll return true. Otherwise, we make it all the way through our loop just like before, and we will return false. Okay, so this is a much better implementation because it takes advantage of the standard library iterators. Now, those of you who are observant will have already noticed that we are passing, when we call this find function, we are passing the list or the vector by value. And this is extremely inefficient because passing by value means we're making a complete copy of all of the elements. We're making a complete copy of that data structure in memory just to use inside of this function. Okay, so rather than just using the vector that we have here inside of main, we're making a copy of it. We're taking the time to make a copy of all those elements, and we're wasting the space to store an entire separate version of this vector just so that we can check what's inside of it. And that doesn't make any sense at all. So it would be a huge improvement just to pass it by reference. And this is a pretty good example of when reference semantics makes sense over value semantics. Okay, no sense in copying the list when all we're doing is just looking, taking a peek inside of it and checking for some item. Okay, but we can actually do even better than this. If you look at where list is used inside of this implementation, right? Where list is used is in two places, to get the beginning iterator and to get the end iterator. We don't actually need the list for anything else other than to get the iterators. And remember, the iterators encapsulate the reference to the elements of the list and how to move through that list. So we don't even need to pass the vector to this function. We can just instead just take the iterators as parameters. So at the call site, rather than passing the vector to the find function, why don't we just get the iterators there, okay, and call the function with those iterators and pass the iterators to the function instead. So rather than taking the list, let's go ahead and say, okay, we want a standard vector of int const iterator. We'll call it it as the first parameter. And then the second parameter will have a standard vector of int const iterator end. That will be the second parameter. And then the third parameter will again be the item we're looking for. Now in our for loop, we don't have to do anything to initialize it. And then all we have to do here is, as long as it is not equal to end, and you'll see that this is the only change we need to make. So if the call site, if the caller of this function gives us those two iterators, we can just use them. Okay, and so long as it is not equal to end, we'll increment it, and on each iteration through this for loop, we will check for the dereferenced value of it. To fix the call site now, let's just go ahead and right here, we'll say standard C begin values. That's the first parameter. The second parameter is standard C end values. Okay, and there we have it. And we should be able to compile again this code and run it. And you will see that the value is found, so everything is still working just as it did before. Okay, so now let's get back to addressing some of those issues. And what I think the most severe issue with the initial implementation that we have, actually the implementation that we have right now, is we're not returning the information about where the item is found in the list. And I think that's critical information we need to return. And now that we have iterators in our implementation, this actually leads to a very elegant solution. So the way the standard library approaches this problem, and there are several solutions to this problem. What I mean is that we want to return two pieces of information: whether or not the item was found, and if it was found, we also want to return the location at which it was found. Okay, and the reason that the using iterators is so elegant is because iterators already encode both of those pieces of information at the same time. That is to say, we can return an iterator that doesn't refer to anything at all if the list doesn't contain what we're looking for. And if the list does contain what we're looking for, we can go ahead and return an iterator that does return to an element. Which element? The element that we were looking for in the list. Okay, so the solution is actually very elegant, and this is exactly what the standard library find algorithm does. All right, so what we're going to do, rather than returning true or false, if it is the iterator that points to the item we're looking for, in fact, what we're going to do is we're going to return this, we're going to return an iterator. So this is the data type now of the return of this function. We're just going to go ahead and return it, because at this point in time, the dereferenced it is referring to the value we're looking for. So at that point, we can just return it. This will return the iterator, which refers to the element we're looking for. And if we make it all the way through this for loop, okay, that means the element we were looking for was not in the list, and so we'll just return the sentinel value. And the sentinel value is the same thing that was passed into the function as the second parameter. All right. So now the find function no longer returns a boolean; it returns an iterator. So let's go ahead and capture that. So it equals the result of the find function. Okay. And what we're going to do is we're going to do the if statement with the initialization. So the first part of the if statement just initializes some value, and then the second part we can put the conditional check. So if capture the iterator from the myFind function, and then the conditional check is if that iterator is not equal to the end iterator. Okay, if it's not equal to the end iterator, that means we've found something. Okay, the value is found. And because we have actually this iterator, we can even go ahead and print out the index at which it was found. So let's go ahead and do that. The value is found at index, and then in order to figure out the actual index, let me just go ahead and add the new line statement at the end. So in order to figure out the actual index, what we can do is we can use a couple other components of the standard library. The distance function, which tells you the distance between two iterators. Okay, so we can take the distance between the begin iterator of this container and the iterator that was returned from the find function. And this will tell us, taking the distance between the begin iterator and the iterator we got back from the function call, will tell us the index at which this element was found in the container. So now that we're using these iterators and we're returning them from the function, okay, now the idea is that we've captured this iterator, and then we can actually make use of it. Okay, so we might want to do something with that object if it was found. If it wasn't found, there's no object to do anything with. So we're just going to stick with that. So let's go ahead and build and run this again. And you will see that the value is found at index 6. And if you look very carefully, here's index 0, 1, 2, 3, 4, 5, 6. So the 2 is indeed at index 6. Okay, and now the last thing I'd like to do, and then we'll be done with sequential search for now, is I'd like to make this a generic function. So right now we're still limited to only being able to work on vectors of int. And what I'd like to at least do is be able to operate on a vector of any kind of element, not just int. Okay, So what I'm going to go ahead and do is I'm going to make this a template. Okay, template, and the type I'm going to vary is the element type. Okay, so I'm just going to name it element type. Why stop there? We could go even further with this. Rather than forcing just a vector to be used, why not also allow the any kind of container to be used? So it doesn't have to be a vector. It could be a stack or uh, any other kind of container from the standard library. So let's also go ahead and let the iterator type, okay, be variable here. And so now we can say all of the iterator types, we'll go ahead and make those one of the template types as well. All right, so let's go ahead and replace the code like this. So now, as long as we're consistent about the iterators we pass in, meaning the begin iterator and the end iterator match, those will also be the type of the iterator returned from the function. And as long as the element type matches what's dereferenced by the iterator, then this function will work. Okay, so I've just made it a template, and you'll see that if I run the code once again, everything will still work just fine. And that is because this template, when it's being instantiated right here, when we call the find function on it, this template is being instantiated with the proper iterator type and the proper value type, okay, or the proper element type. And the real proof that this works would be to then go ahead and change this to be an iterator of characters instead of an iterator of integers. Let's go ahead and just do a, let's just go ahead and replace these ints with some characters. And then let's go ahead and look for the W character, the W character. Okay, so now this is a vector of an entirely different type. Okay, so now we have a vector of characters, and now let's go ahead and build and run this program. And we will see that everything works still just fine. That W is at position 7 in this list. Okay, and it works because we've made the element type and the iterator type now generic. Okay, so now we're getting pretty close to what you might see in the standard library's find function. There are a few more additional improvements that it makes, but I think we've pretty well exhausted the types of things that we can do with this algorithm. And congratulations, you've just implemented a really good sequential search algorithm.